Hello and welcome to this video tutorial for Parametric version 3 and ANSYS Mechanical. The content of this tutorial is rotational effects and modal effects. So in Creo I have this fan part that I believe we've used for some CFD analysis. While it's important to assess the effects of fluid loads on this fan, it's also necessary to rotate this in a structural sense and assess any stresses, strains or deformations that result from rotational inertial effects. So I've imported this part into ANSYS Mechanical and I've meshed it, a fairly crude, quick and dirty mesh. However, when I go to apply loads and restraints, so you've seen there's pressure loads, force loads, bending moments. We can also apply inertial effects. So this is useful if we wanted to apply acceleration. So if we have a large component, we want to assess the self-weight due to gravity, we can apply that. We can also apply rotational inertial effects. So I'll select the entire body of our fan. Instead of defining our rotational load by magnitude, I'll go by components. I always find it easy to work in components. And in the x-axis, we'll apply a rotational load of 628 radians per second. So pretty quick, equal to 6,000 RPM. And I'll keep the y and z axes 0. So you can see our fan has been built aligned to the x-axis, which makes it much easier for applying these loads. Okay, I'm also going to fix the end of this in supports with a fixed support. I'll apply that. That just gives this model enough boundary conditions so that our ANSYS solver can provide the non-trivial solution. Okay, with that in mind, I will right click and solve that. We can assess our deformations. So we can animate that. So of course that's an exaggerated scale, but you can imagine these blades, these fan blades, twisting inwards due to the rotational inertial effects. We can also look at our stresses, and this makes sense too, that our highest stresses are at the blade root due to the centrifugal effects. Okay, that's quite a quick overview, but we can take this analysis one step further. So often in the design of rotating equipment, you want to avoid any natural frequency excitation. This could be quite disastrous if the fundamental mode was equal to the rotational frequency of our device. So back in Workbench, we can select our Modal tool. We want to share the geometry in the model and not the solution for the time being. Okay, so our static structural model is now linked to a modal response. And if we open ANSYS Mechanical, we can see this modal tab appears in our work tree. So we can, in our analysis settings, for example, we can find the first 10 frequency modes. I will also apply a fixed support. We can now solve this. So you can do a modal analysis for any structural component. And if we have a look at our results, we'll assess our deformation. So we have our first mode, twisting of our blades. These deformations here are essentially meaningless when we're talking about our modal response. It's just the normalized length of our fan blade. And we can look at higher order modes. So we could change that to mode 7. We can evaluate that. Okay, so we know the operating frequency of our fan is 628 RPM. None of these modes coincide with that, which is good. However, as our blade accelerates from 0 to say 6,000 RPM, it could pass through some of these modes. And we can assess that by using what's called the Campbell diagram. So as a final step, we'll add rotational load. Selecting our body here. We'll apply components. And in our analysis settings, our solver is going to be damped. We're going to turn Coriolis effects on. And we're going to produce a Campbell diagram. We're going to use four analysis points. Okay, it's giving us a question mark for our rotational velocity. We can then apply in tabular form 4 different rotational velocities to simulate the acceleration of our fan. So our first speed is 0, our fan's stationary. The next speed is equivalent to 2000 RPM. This is in radians per second. 4000 RPM. And then our rated speed of 6,000 RPM. So we'll now solve this. And what our solver is doing is taking each of those speed inputs from 0 to 6,000 RPM, formulating our fundamental modes, and then we can plot that in graphical form. So if we add a Campbell diagram here, and evaluate that. This takes a little bit of interpretation, but in the dark black line is a 1-to-1 ratio of our rotational velocity and the frequency of any fundamental modes. And then we have these 10 modes that I plotted. So you can see as our fan accelerates from 0 to our desired operating speed, there's 2 instances called critical speeds where the rotational frequency of our fan matches a fundamental mode. And this is highly undesirable or potentially dangerous, and you want to avoid that. So in some cases it can be unavoidable to pass through these situations as long as you do it quickly, but you wouldn't want your fan operating around these speeds for any extended periods of time. Another interesting point here is that some of these modes are shifting in frequency, so they're actually increasing. This is due to an artificial stiffening effect that occurs due to rotational inertial effects. It induces stiffness in the structure, which increases our fundamental modes. So the Campbell diagram is quite a useful tool for analyzing our rotational equipment and making sure that they don't coincide with any natural frequency effects. So putting this in summary, we imported our model from Creo and meshed it. We then did a static structural solver applying a simple rotational velocity to see any stresses that were formed. I then looked at a modal analysis using a Campbell diagram where I applied multiple rotational speeds to assess any natural frequency excitation.